Okay. Now, what is this? This is just the trace of x transpose inverse, right. So, this is what it is. This is the quantity that we are focusing on. Now, let the trace, remember the trace is just the sum of the diagonal entries of a matrix, right. So, if you have a matrix with diagonal entries A1 to AD, then the trace of A is just sum over I equals 1 to D AI. It is just the sum of the diagonal entries. So, somehow the diagonal entries seem to play a role of this covariance matrix. Okay. So, the trace also happens to be the sum of the eigenvalues of the matrix, right. So, this is also same as sum over I equals 1 to D lambda I, where lambda I is the ith eigenvalue of A, right. So, this is a standard result about matrices, that the trace, the sum of the diagonal entries is same as the sum of the eigenvalues of a matrix. Of course, if this can be got from the characteristic equation and so on, but we will not try to derive this. So, we will assume this is a fact that we know. So, how does that help us? Well, that is telling us that let the eigenvalues of x transpose inverse be, let us say the eigenvalues are lambda 1 dot 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 lambda d. Let us say these are our eigenvalues of the matrix that we care about, right. So, or rather let me say, to make the discussion simpler, let us call the eigenvalues of x transpose, the covariance like matrix, as lambda 1 to lambda d. Now, here is a question that you can pause and think about. Now, what would be the eigenvalues of x transpose inverse? What can we say about the eigenvalues of x transpose inverse? Well, the eigenvalues of the inverse of the matrix are just the inverse of the eigenvalues themselves, the reciprocals, right. So, which means this would be 1 by lambda 1 dot 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 1 by lambda. These would be the eigenvalues of the inverse matrix. So, which means that the mean squared error, right. So, which is what I mean, the one that we have here is just the mean squared error, because it is the average squared deviation between our estimator and the truth, can now be written as the mean squared error can now be written as of w hat ml, which is just the expected value of norm difference between w hat ml and w squared, can now be written as understood as sigma squared into sum over I equals 1 to d 1 by lambda I. This is simply because we are assuming that lambda i's are the eigenvalues of x transpose. So, the inverse will have 1 by lambda i's, and then the trace is just the sum of these. Okay. So, now here is what we are going to do. I am now going to pull a new estimator out of the hat and ask you to consider that for a moment, right. So, for the moment, let us not worry about how I got this estimator, we will come to that later. But let us say here is an estimator that I give you, I ask you to consider, right. So, consider the following estimator. So, basically we are trying to get some kind of a better estimator, and let us see if the estimator that I am asking you to consider is in fact better or not, right. So, here is an estimator. Let us call this w hat nu, which is not the maximum likelihood estimator, it is going to be different, and it looks like the following. So, it is x transpose plus some lambda times the identity matrix, the inverse x y. Now, what have I done? Lambda is just some real number. Let us even say this is a positive real number. I is just a matrix which is a D cross D matrix, identity matrix, which diagonals as ones, right. So, if you want to compare this with our w hat ml, remember w hat ml was just x transpose inverse x y. Now we are saying inside this we are adding one lambda I. Let us see what that gives us. How does that help us, right? So for some matrix, so for some let us say for some matrix A, let us say any matrix A, let the eigenvalues be lambda 1 to lambda d. In our case we are looking at XX transpose, but in general that think of some matrix A, right. So now what are the eigenvalues of A plus lambda I, this new matrix? What are the eigenvalues of these? Well, if you remember the definition of eigenvalues, the eigenvalue definition was as follows, right. So A v equal to lambda v, lambda 1 v. That is why okay, A v1 equal to lambda v1, which means that v1 is an eigenvector with an eigenvalue lambda 1. Now, what would then A plus some lambda I times v1 be? Well, that would be A v1 plus lambda v1, but A v1 we know is lambda 1 v1 plus lambda v1. So, this would be lambda 1 plus lambda times v1. So, which means v1 is also an eigenvector of A plus lambda I now, but with eigenvalue lambda 1 plus lambda. So, you are adding lambda to the eigenvalues, right. So, these eigenvalues then are going to be just lambda 1 plus lambda dot 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 lambda d plus lambda. These are going to be the new eigenvalues. So, what are we going to gain by this? Well, at a high level, now if originally the quantity that was affecting the mean squared error was the trace of XX transpose inverse. Now we have changed that somehow to XX transpose plus lambda I inverse XY, right. So, which means XY is the estimator, which means that we somehow should expect the trace of XX transpose plus lambda I inverse should affect our mean squared error. Now, what would be the trace of this? Well, we have assumed that lambda 1 to lambda d are the eigenvalues of XX transpose. We know what are the eigenvalues of XX transpose plus lambda I, lambda gets added to each eigenvalue, which means the trace of the inverse would simply be sum over I equals 1 to n 1 by lambda I plus lambda, right. So, this gets added. Now, what is the advantage of this is that, well, intuitively speaking, so the reason one reason why your mean squared error could have been really large is because either your sigma square is really large, which you cannot really do anything about, but it could also be the case that your trace of XX transpose inverse was very large. Now, what we are saying is that, well, why would the trace of XX transpose inverse be very large, which means that the lambda i's, right. So, the eigenvalues are small. Because they are small, their reciprocals are large, which means that this second quantity here might be large, and so the mean squared error is large. Now, what we are saying is that we want to make the second quantity smaller. So, we are artificially introducing this extra lambda I here, such that now the hope is that the trace of the mean squared error is going to depend on the trace of this new matrix, which is XX transpose plus lambda I inverse, which adds a lambda to the denominator, right. So, which means that you are increasing the denominator of each of these, which means the eigenvalues have increased, and so the denominators have increased, and so the quantity itself has decreased, which means that overall this quantity has gone down, right. So, the hope then is that, well, this will hopefully overall reduce our mean squared error, right. So, this is not the, this is just an intuitive argument as to why adding this might potentially decrease our mean squared error, right. So, if this happens, then we are happy. So, so now is this always true? Does this always happen? Well, the interesting result is the following existence theorem, which we won't really prove, but then it's good to know. The following theorem says So, we'll make an informal statement. So, there exists some lambda in R such that the W hat nu, which is defined as XX transpose plus lambda times I inverse XY, has lesser mean square error than W hat ML. The existence theorem says that, well, there should exist some lambda such that instead of using W hat ML, if I used XX transpose plus lambda I inverse XY as my new estimator, then this would have lesser mean squared error, right. So, on an average, this is a better estimator than the original estimator. The problem is, though, this is an existence theorem. It just says that there exists, this is the condition, right. So, there the symbol for there exists some lambda such that this is true. It does not tell us how to find this lambda, right. So, because this lambda will depend on your data itself, right. So, in general, there may not be a way to automatically find this lambda. So, then how do we find this lambda? Well, in practice, what you can do to find lambda is the following. In practice, find lambda by a procedure called cross validation, and this is a very common procedure. We will talk a lot about this procedure as we go along. So, what is this cross validation procedure? Well, here is what it is, right. So, we do not know what is the lambda that performs well, right. So, in the sense that what is the lambda that will give us better accuracy on the training set. So, what you could do is you can compute, you can basically divide your entire training set. You have x1 to xn, let us say you had 10,000 points, you divide it into what is called as a train set and what is called as a validation set. Let us say this was 80% of your data that you have and this is 20% of your data that you have. Now, what you do is you find your W hat modified or W hat new on the train set, right. So, train on the training set and check for accuracy on validation set. What does that mean? That means that I take only the data from the training set and then I compute this estimator XX transpose plus lambda I inverse XY for some choice of lambda, and then I see how good is this choice of lambda by getting this estimator and then making predictions for the X in my validation set and comparing with the actual Y, right. So, then that well, check for accuracy or check for error, right. So, we can think of this as error also, right. So, accuracy would be more for a case where you have a finite number of predictions. Here you can think of it as how much error does your computed W hat new suffers with respect to the validation set, right. So, now for different choices of lambda you might get different errors and then you pick the one that has the least error, right. So, this is what you would do and pick lambda that gives least error. So, this procedure is called as validation because you are keeping aside some data as if it is a proxy for the test data that you will encounter later. Your goal is to do well on the test data, but you do not have the test data with you. So, you create this mimic the test data by keeping aside some part of your training data for testing, which we will call as the validation set. Train only on the training set, get your W hat new and then for various choices of lambda and see how it performs on the validation set. Now, what might happen is that the question is how can I split, what is the right way to think of which 80% goes to the training and which 20% goes to the testing. You can do it at random, but then well you might get unlucky and then the 20% in the validation set might not be representative of what you are learning from the 80% in the train set. So, your lambda accuracy or error that you are looking at may not be actually representative of the true error. So, to avoid this, what people do is what is called as a k-fold cross validation, which kind of does the following. You do cross validation multiple times, right. So, you have your data, you divide it into k parts, k folds. Let us call this fold 1 f1 f2 dot 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 fk. You have k folds, basically divide your data into equal parts, k different parts. If you have 10,000 data points, if you have 10 folds, each fold gets 1000 data points. Now, what you do is train on folds f1 dot 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 f some I minus 1 fi plus 1 dot 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 fk, right. So, validate then on fi. So, you keep one fold aside for validation, train on the remaining for every choice of lambda and validate on the fold that you have left aside. Now, you can, because there are k folds, you can leave aside k folds one at a time. So, there are k different data sets that you can train, validation sets that you can create. Let us say if k is 3, then f1, f2 for training, f3 for validation is one fold, one way of dividing. F1, F3 for training and F2 for validation is another way, and F2, F3 for training and F1 for validation is another way, right. So, now for every choice of lambda, you see how you perform on the left out fold and then average these errors, and whichever lambda gives you the least average error, then you pick that lambda, right. So, pick lambda that gives least average error. So, such a procedure is called k-fold cross validation. Now, the question then comes is how do you choose k, right. So, if I have 10,000 points, how can I decide to divide it into 10 parts or 20 parts? Now, in general, larger the k the better, because you are averaging over multiple possibilities. In fact, in the extreme case, you can even do what is called as leave one out cross validation. Leave one out cross validation, where you have n data points, you train on n minus 1 data points and see how well your trained model does on the nth point, the point that you have left out. But in general, if you have billion data points, you cannot do leave one out cross validation, because you have to create billion different train validation splits and then average up over everything, and that is computationally going to be a nightmare. We cannot do that, right. So, in practice, you choose k depending on how much time and resources you have, and then you average over everything else, right. So, that is the process of cross validation to find this lambda, and the hope is that such a lambda will actually perform well on the test data as well with this new modified estimator. Okay. Now, one question that still lingers in our minds is the following, right. So, we said this w hat nu is x transpose plus lambda I well inverse x y. Of course, we made the argument that this is used to reduce the mean squared error in some sense, and then there is some lambda for which the mean squared error goes down and so on. But is there an alternate way to understand this, right? So, how would I have started thinking about this problem that would have led me to such an estimator in a more principled way, right? So, can we come up with a principled way to get this estimator? That is what we will ask next. So, is there an alternate way to understand this? Well, it turns out the answer is yes, and it is not something that we have not seen earlier. It is something that we already have seen as a procedure to get alternate estimators, but we looked at it in an unsupervised context. Now, we are going to look at it in a supervised context. I am sure many of you have already tried to guess this. If not, try to think about what other alternate ways to maximum likelihood that we used in the unsupervised learning context when we are dealing with probabilistic modeling. We are going to do something similar here.